Now consider the heat equation problem for a finite interval ut minus k into uxx equal to 0 where 0 less than x less than L, t greater than 0 with the boundary conditions u at 0 t equal to u at L comma t is equal to 0 where t greater than 0 and the initial condition u at x0 at time t equal to 0 is equal to f of x where 0 less than x less than L. So this is the initial and boundary value problem for the heat equation. Okay, heat equation is given by ut minus k into uxx equal to 0. So here the interval is finite. That means it varies from x equal to 0 to x varies from 0 to L or x belong to open interval 0 comma L. Now the boundary conditions are at x equal to 0, u at 0, t is 0 and at x equal to L, ult is equal to 0. And the initial condition u at x0 is equal to f of x where f is the given initial condition and k is a positive constant. Okay. Now, in order to make these equations are numbered as 1, 2 and 3 respectively. And in order to make the equation 2 consistent with equation number 3, we have to choose f of 0 and f of L as equal to 0. This is because from equation 3 we have it is given u at x0. Time t equal to 0, ux0 is equal to f of x. Then u at 0, 0 will be f of 0. And in equation number 2, from equation number 2, we have u of 0 t is equal to what? 0. So u of 0 t is equal to 0 from equation number 2. And then when t is equal to 0, we have u of 0, 0 equal to 0. And from equation number 3, we have u at 0, 0 is equal to f of 0 and u at lt. And in the equation and from equation number 3, u at 0 u at L0. U at L0 is equal to f of L. And here from equation number 2, u at L0 equal to 0. So in order to make this equation number 2 compatible with equation number 3, we have to choose f of 0 equal to 0 and f of L is equal to 0. So this we have to choose. Okay. Now this problem represents the problem correspond to the evolution of the temperature u of xt in a homogeneous one-dimensional heat conducting rod of length capital L such that the rod is very narrow and it is laterally insulated whose initial temperature at a time t equal to 0 is known, that is given by f of x, and that its two ends are immersed in a zero temperature bath. Okay, so this problem represents the heat conduction. Okay, heat conduction of a rod of okay, so there is a rod okay, so this is a rod of length L and heat is conducted along this rod, and this is laterally insulated rod. So this rod is laterally insulated, and along the direction of heat passing we are taking it as the x-axis, and the t-axis, the time t is taken along the vertical axis. So this is the point x equal to 0. Sorry, here we are taking t. So this is the point t x equal to 0, and this is the point x equal to L. This is the x-axis. This is the point x equal to L. So along this rod, heat is conducted, and This represents the heat conducting problem along the rod of length capital L. We also assume that there is no internal source that heats or cools the system. Now a diagrammatic representation is as shown in the figure. Now the rod is of length L, and along the heat direction we are taking is as the x-axis, and along the time we are taken as the t-axis. And when t is equal to 0, t equal to 0 means it is the x-axis. We have u of x 0 is equal to f of x, and along x equal to 0, that is the t-axis, u equal to 0, and along when x is equal to L, when x equal to L also u is equal to 0, or u of L comma 0, L comma 0 is equal to also equal to 0. Okay, so when x is equal to u of lt is also 0, and u of 0t, when x is 0, that is t axis, u of 0t is equal to 0, and u of lt equal to 0, that means along x equal to L, this is the line x equal to this is the line x equal to L, and along this line we have u is equal to 0. So along x equal to t x equal to 0, and along x equal to L, u, the value of u is given as 0. So this is the diagrammatic representation. Now the heat equation is inside this region. Heat is inside this region. That is ut minus k into uxx equal to 0, the homogeneous equation. One-dimensional heat equation ut minus k into uxx is equal to 0. So this is the diagrammatic representation of the initial boundary value problem for the heat equation together with the domain 0 less than x less than L. Okay. Now, the problem 1 to 3 is the initial and boundary value problem, which is linear and also homogeneous. The boundary condition 2, that is the conditions u at 0 t is equal to u at L t equal to 0. The conditions at the endpoints, that is u at 0 t and u at L t, the temperature at x equal to 0 and x equal to L is equal to 0, and this condition is known as Dirichlet condition. This is known as the Dirichlet condition. Okay. So this is about the problem. Now we seek for a solution which is in the form of u of xt. Now we try to solve this heat equation. So we seek a solution u of xt by the method of separation of variables. By the method of separation of variables, that is u of xt. U of xt is of the form x of x into t of t, product of the variables x of x into t of t, where x and t are functions of x and t respectively. Capital X is a function of small x alone, capital T is a function of small t alone. So that the solution of the problem 1 to 3 is u of xt is equal to x of x into t of t. And we also assume that is 0, so the solution must be non-zero, because we are not interested in the 0 solution. We need to find a non-trivial solution. We are not interested in the trivial solution. So we assume that u of xt not equal to 0, or we avoid the cases where u of xt becomes 0. So we seek the functions capital X and so therefore we seek the functions x and t that do not vanish simultaneously or identically. That do not vanish identically. Okay, let this be equation number 4. Now differentiating equation number 4 once with respect to equation number 4 once with respect to t and twice with respect to x, and substitute these derivatives into the given PDE 1. So first of all we have to find ut and uxx. So ut differentiating with respect to t, we can consider x as a constant because it is a function of small x alone. So this ut will be x into t dash, or we can write it as x into tt, dou capital T by t, like this. So ux is x dash into t, uxx will be x double prime into t, or capital X dou square capital X by dou x square. So xx implies dou square capital X by dou x square, or since it is a function of x alone, we can write it as d square x by dx square, and ux as tt. T is a function of t. Tt means d capital T by dt. So these are the notations, and which can be simply written as x suffix is double x. Now substituting this in equation 1, we have ut minus c square into uxx is equal to ut x t dash minus x t square minus not c square, it is k. The constant is k, sorry, it is k. So x t dash minus k into uxx. Uxx is x double dash into t equal to 0, or x t prime is equal to k into double x into t, or we can write it as t prime by kt is equal to x double prime by x, or tt by kt is equal to x double prime by x. Now since small x and small t are the independent variables, we can write this differentiating this one with respect to t implies that there is a constant, there exists a constant denoted by lambda, which is called the separation constant. So this can be written as this is equal to since small x and t are the independent variables, this must be equal, where capital T is a function of t alone and capital X is a function of x alone, and this must be equal if and only if this is equal to a constant, and we are taking that constant as minus lambda, where lambda is a constant, and this is known as the separation. Lambda is known as the separation constant. Lambda is called the separation constant. Okay, now we first consider the ODE, ordinary differential equation. X double x by x is equal to minus lambda. That is x double x is equal to minus lambda into x. x double x means d square x by dx square plus lambda x equal to 0. This is an ordinary differential equation. Ordinary differential equation where 0 less than x less than L. And also if we consider the second one, that is t dash by tt by capital K t is equal to minus lambda, or d capital T by dt is equal to minus lambda K into capital T, or d capital T by dt is equal to, this is equal to d minus lambda K into capital T, where T is greater than 0. Okay. Now the function u satisfies the boundary conditions. Now consider the boundary conditions. U at 0 t equal to u at L comma t is equal to 0. That is x of 0 into t of t equal to 0, and this is equal to, and x of L into t of t equal to 0. So from these conditions, either x of 0 equal to 0 or t of t equal to 0, and from this x of L equal to 0 or t of t equal to 0. But u is a non-trivial solution, but we need a non-trivial solution. Okay. Or since u is a non-trivial solution, or since u is not a trivial solution, u equal to 0, it follows that, or we have from the first equation the only possibility is x of 0 equal to 0, and from the second one we have x of L equal to 0. Hence the problem is, the function x should be a solution, or should be a solution of this of the boundary value problem. So the equation together with these boundary conditions, capital X of 0 equal to 0 and a capital X of L equal to 0. So this should be X should be a solution of the boundary value problem of the ODE. D square x by dx square plus lambda x equal to 0, where 0 less than x less than L, x of 0 equal to x of L equal to 0. So this is the problem. Now we have made two ODEs. One is d square x by dx square plus lambda x equal to 0. Let this be equation number 5. And the other one is dt by dt equal to minus lambda k into capital T. And let this be 6. So equation 5 and 6 are the system of ODEs to which it is reduced. And then so this will be the equation 5 with the initial boundary conditions, that is 7. Okay. So first of all we need to find a solution for the a non-trivial solution. We need to find a non-trivial solution for this system. For this system 5 and 7, such a function is or non-trivial solution is known as the eigenfunction of the problem with an eigenvalue lambda. So the value of lambda for which this system 5 and 7 has a non-trivial solution is known as eigenvalue. So lambda is an eigenvalue. Now a non-trivial solution of this system. A non-trivial solution of this system 5 and 7 is called an eigenfunction. Is called an eigenfunction of the problem with an eigenvalue lambda. Okay. And this problem is known as the eigenvalue problem. The problem 5 and 7 are called the eigenvalue problem. Are called the eigenvalue problem. Okay. So the eigenfunction means it is a non-trivial solution of the system 5 and 7, and the system 5 and 7 is called the eigenvalue problem, and the value of lambda for which the system has a non-trivial solution u is called the eigenvalue problem. Now we will try to solve the system 5 and 7. The system is a boundary value problem, boundary value differential equation, boundary value problem, and it is an ordinary differential equation with the constant coefficients. Equation 5 is given by the equation with the constant coefficients. And we know that there exists a solution. We don't know whether it exists a solution for any value of lambda, but we need to check for that, for which lambda there exists a solution, and also that also satisfies the given boundary conditions that we need to check. And we also assume that the lambda is real, the eigenvalues are real. Okay. So now this is a second order PDE, and we consider each case for lambda equal to 0 and lambda is positive and also lambda is negative. And first we find a general solution, and then we sort the solution that also satisfies the boundary conditions. Okay. Uh, so for that, before moving to the solution, we assume that so here we assume that lambda is real. Okay, lambda is real. Okay. So the equation 5 given by d square x by dx square plus lambda x equal to 0. This is a second order homogeneous ordinary differential equation with a constant coefficients. So here the coefficient of the leading term is 1 and coefficient of x is lambda. There is no term containing d capital X by dx, first order term. Okay, first degree term. So for different values of lambda, we find the general solution of this equation number 5. So case 1, we consider it lambda equal to 0. So when lambda equal to 0, we have the equation reduces to d square x by dx square equal to 0. Now integrating this, we get x of x is equal to some c1x plus c2. Now apply the boundary conditions. X of 0 equal to 0 implies C2 equal to 0. Therefore, x of x equal to C1x. X of x is equal to C1x. Now x of L equal to 0 implies uh, x of L equal to 0. It will imply that um, x of L, C1 into L equal to 0. But L is the length and it is not equal to 0. We have C1 equal to 0. Therefore, x of x equal to 0. This will imply that U equal to 0 identically. U identically equal to 0, which is a trivial solution. So when lambda equal to 0, we obtain only the trivial solution, but that we are not of interested. But we are not interested of a trivial solutions. Therefore, lambda equal to 0 is not an eigenvalue of the problem. So lambda equal to 0 is not an eigenvalue. Okay. Since we are not interested in the identically zero trivial solutions. Now second case or case 2, assume that lambda is negative, lambda is less than 0 or negative eigenvalue. Then negative, that is negative eigenvalue. So when lambda is negative, we have d square x by dx square plus lambda x equal to 0. Therefore, the auxiliary equation is some m square plus lambda equal to 0. So, m square equal to minus lambda. Since lambda is negative, minus lambda is positive. Therefore, m is equal to plus or minus root of minus lambda. For root of minus lambda is positive and hence this root exists. So m1 equal to root of minus lambda, m2 equal to minus root of minus lambda. Therefore, the general solution is given by x of x is equal to some c1 into e raised to root of minus lambda x plus c2 e raised to minus root of minus root lambda x. So this will be the solution. Now x of 0 equal to 0 implies c1 into 0, that is c1 plus c2 equal to 0. Now x of L equal to 0 implies c1 e raised to root of minus lambda L, c2 e raised to minus root minus lambda L equal to 0. Now this represents a system of equations. Let this be equation number 8. So 8 represents a system of equations in the unknowns C1 and C2. So when we consider this in the form sum Ax equal to 0 like this, that is, we can write the system as 1 1 e raised to root of minus lambda L e raised to minus root lambda L into C1 C2 equal to is a homogeneous system of equations. Matrix system Ax equal to 0. Now let this be the matrix A such that determinant of A, therefore det of A is equal to, or where determinant 1 1 root of minus root lambda L e raised to minus of root of minus lambda L, which is equal to e raised to minus root minus lambda L minus e raised to root of minus root lambda L, which is not equal to 0. Now since det of A is not equal to 0, det of A not equal to 0 implies the system Ax equal to 0, or AC we can write C as matrix C1 C2. So the system AC equal to 0 has a unique solution. Since C1 C2 equal to 0 0 is a solution, is always a solution of this homogeneous system, that is the trivial solution, and is a unique solution, that is the trivial solution. U identically equal to 0. Sorry, trivial solution not U equal to 0. C1 equal to C2 equal to 0. Therefore, x of x is identically equal to 0, which in turn implies, so this will also give a trivial solution. U equal to 0. Therefore, when lambda is negative, then it is not an eigenvalue. Now we need to consider the last case, case 3, that is lambda is positive. Then the auxiliary equation m square plus lambda equal to 0 would imply that m square equal to minus lambda. So m is equal to root of plus or minus root of minus lambda, that is plus or minus root lambda into I, where root of lambda is positive. Therefore, the two solutions are what? Y1 of x is equal to sine of or cos of root lambda x, and y2 of x is sine root lambda x. Therefore, the general solution x of x is equal to c1 cos root lambda x plus c2 into sine root lambda into x. Now substitute the boundary conditions. X of 0 equal to 0. X of 0 equal to 0 means C1 into 1 plus C2 into 0 equal to 0. This will imply C1 equal to 0. Therefore, x of x will be reduced as C2 into sine root lambda x. Now the second boundary condition x of L equal to 0 implies C2 into sine root lambda L equal to 0. So if C2 also equal to 0, we will get only the trivial solution. Therefore, this must imply sine of root lambda L must be equal to 0. Since C2 equal to 0 implies U equal to 0. X will be 0. That means in consequence U equal to 0. That is the only trivial solution. So this must imply that sine of root lambda L is equal to 0. That means sine of x equal to 0 only if x is equal to n pi. So root lambda into L. Root lambda L equal to n pi where n equal to 0 plus or minus 1 plus or minus 2 etc. Okay. Uh, So when n equal to 0, that is lambda equal to 0. But when lambda equal to 0 is not an eigenvalue, so we can avoid or exclude that 0. So root lambda L equal to n pi for n equal to plus or minus 1 or n equal to 1, 2, 3, etc. This is because when we are considering lambda, we have n pi by L the whole square. Okay, so we can avoid the negative values for n. We are considering only the positive values. So the eigenvalues, possible eigenvalues are lambda is equal to n square pi square by L square. Sorry, this L is actually, this is capital L because we have taken it as the length of the road, that is capital L. So that is for n equal to 1, 2, 3, etc. That is lambda can be, when n equal to 1 it is pi square by L square. When n equal to 2 it is 4 pi square by L square, etc. So these are the possible values of lambda, that is the eigenvalue. So these are the eigenvalues. So these are the eigenvalues. Now the eigenfunction is given by x of x. X of x is equal to C2 into sine root of lambda n pi by L x. Okay. So which are uniquely defined up to a multiplicative constant. So we can like this, or therefore the eigenfunctions the eigenfunctions of functions are, we can write it as x of x is equal to sine n pi x by L. Okay, corresponding to the eigenfunctions, sorry, eigenvalues, lambda equal to n pi by L the whole square. Okay, where n equal to 1, 2, 3, etc. and these are uniquely defined up to a multiplicative constant. Now, the set of all solutions is an infinite sequence of set of all solutions of the given problem or of this problem 5 and 7 is an infinite sequence of eigenfunctions, each associated with a positive eigenvalue. The possible eigenvalues are here pi square by L square, 4 pi square by L square, like that. So it is convenient to use the notation xn of x is equal to sin n pi x by L with lambda n, the eigenvalues n square pi square by L square, or we can write it as n pi by L the whole square for n equal to 1, 2, 3, etc. Okay. Now, so this about the eigen functions. Now, so for our first the ODE in the system of two ODEs is solved. Now we need to calculate T of T or the function T as in terms of small t, and then we need to find the general solution or the separate solution of the form x of x into T of T. Okay, that we will discuss in the next lecture.